Hello, this is Mr. Collier, and today we're going to be looking at classifications of number, rounding, and significant figures. Okay, so first of all, let's take a look at the different sets of numbers out there. First of all, real numbers include all of these numbers we have here. Integers, represented by z, is the set of the positive whole numbers and negative whole numbers, and 0 all included. So it contains all those numbers. Now z plus is a set of positive integers, so that's 1, 2, 3, and so forth. Also sometimes called the natural numbers, but you can represent that as z plus. And of course, z minus is negative 1, negative 2, negative 3, and so forth. Okay, all the negatives are the whole numbers. So that's not including fractions and things like that. Okay, so Q is for rational numbers, so that does include things like fractions and decimals. Like 0.27 is a rational number, but not an integer. And sometimes n is used to represent the positive integers. Q is a set of rational numbers. Okay, we already said that. And this here is Q prime. Okay, that's a set of irrational numbers, so things like pi, root 2, root 3, root 5, that cannot be written as a fraction. Basically, when you put these things in your calculator, you get decimals that continue forever without repeating. So those will be irrational numbers. Okay, here's a diagram of these. So rational is represented by Q, irrational is Q naught, or Q prime. It's not rational, so it's irrational, these numbers like this. Rational numbers include fractions and terminating decimals or repeating decimals like this, positive and negative. Also, numbers inside here, these are also rational numbers. So anything inside is also rational. So integers include like numbers like this, the negative numbers, and as well, and whole numbers include 0, 1, 2, 3, 4, 5, 6. So those are called whole numbers. And natural numbers are sometimes called the numbers 1, 2, 3, 4, 5, so not including 0. So a natural number here, we could call this z plus. So that's the positive integers. And integers are represented with z. Okay. Okay, so let's do the following examples next. Is negative 3 a natural number? No, that's false. Natural numbers include only the positive integers. Is 3/4 an element of the rational numbers? Yes, that's true. Okay, if a number can be written as a fraction of two integers, then it is a rational number. This next number, is that a rational number? Well, it's a decimal that continues forever, but it does repeat. So repeating decimals are rational numbers. You can write that as 1/3, right? This equals 1/3. So this is true. Is root 2 a rational number? No, that cannot be written as a quotient of two integers, so that is false. Is 2 1/4 a real number? Yes, true. So all these numbers are real numbers, including pi. Is pi not an element of the real numbers? That's false, because it is an element of the real numbers. Okay, the only numbers that are not elements of the real numbers are numbers like root -1. That would be not a real number. That's the main example. Okay, is root 3 a rational number? That's false. Cannot be written as a fraction. Root 4 can, because root 4 is 2, and that's a real number, or a rational number. Is 0 a member of the positive integers? That is false. It's not a member of the positive integers. They start off at 1. Is 3 not a real number? That is false, because 3 is a real number. Negative 4.7, is that a member of the integers? That is false, because integers do not include fractions or decimals. They're only like -3, -4, and such like that. Okay, next we're going to be rounding some numbers. So we'd look at the digit after the one you want to round. If the digit being rounded is less than 5, keep it the same. If it's 5 or more, round up. So we round to nearest 10 here, so the 10 value is 7 here, and we have to look at the number after, which is 8. 8 is above 5, so we round up to 80. Here the 10's value is 5. We have to look at the 1. The 1 is less than 5, so we keep it the same. 1650. Okay, next we're rounding to nearest thousandth, so let's identify the thousands here. It's 10, ones, tens, hundreds, thousands. So when we round this number, we look at the 4. 4 is smaller than 5, so we keep it the same. So it's 123,000. Let's take a look at the 5. So are we rounding the 5? So we look at the 4. 4 is less than 5, so it stays the same, 5,000. Round off to the number of decimal places indicated. So 2 places after the decimal, so it means here. We're looking at that number. We look at this number. It is 2 is less than 5, so we round that to 5.36. So 2 places after the decimal, that means we're going to round here, and we look at the 8, it's going to be 0.01. Here, we'll look at the second decimal place here, and the number after that is a 9, so that means we round up to 9.05. Okay, sometimes we have to round to a certain number of significant figures, which is very different than rounding that we did previously. Each number to the right is another significant figure, except for end zeros that have no non-zero numbers after them. Okay, let's take a look at some examples. So in all of these, the first significant figure is 9, so there's 5 significant figures here. We count zeros in between. Here there are 4 significant figures. Okay, we include that 0 at the end. We include zeros at the end of a decimal, but not at the end of a number without a decimal. So here there's 2 significant figures. Okay, how many significant figures are there? We don't count zeros at the front, so there's 3. Here we count zeros in between, so this is 6 significant figures. Don't count these zeros in the front, we count this 0 at the end. So that's 4 significant figures. Okay, so let's take a look at this. Round significant figures, always use the same rules as general rounding. Look at the number after, and so forth. If 0 to 4, round down. If 5 to 9, round up. So round to the number of significant figures in the bracket. So 2 significant figures. So that means we would have to look at, or round this number. We'd look at this one here after it, which is higher than 5. So we round this up to 15,000. That's 2 significant figures. Here 2 significant figures means we just have these 2, so we need to look at this one here, which is less than 5, so we keep it the same, 0.0079. Okay, so when we round measurements, there is error always, right? The measurement is only accurate to like half the smallest division on the scale. So if you use a ruler that's marked with millimeters and you measure like 50 millimeters, that means it could be up to 50.5 millimeters or 49.5. So the accuracy is, well, you could say, how can we state this? We could state it as plus or minus 0.5 millimeters, right? When you get your answer, it could be within plus or minus 5 millimeters. Your accuracy here could be with a centimeter rule, it's plus or minus 1 centimeter. Okay, so let's take a look at this example. State the range of possible values for each of the measurements given that they were taken using the device and bracket. So tape measure marked in centimeters. So the actual measurement could be anywhere from 127.5 centimeters to 128.5 centimeters. Okay, and maybe we'll write this more precisely. It could be anywhere from the, we'll call it length or something. It could be anywhere from 127.5 centimeters. It could be equal to that actually, and it could be anywhere up to 128.5 centimeters. Okay, if it was exactly 128.5 centimeters, you'd round it up to 129, so it can't be equal to 128.5. Okay, so next we have 300 milliliters measuring cup marked with 100 milliliters. So that could be anywhere from 250 milliliters to 350 milliliters, right? Now it can't be exactly 350 or you'd round up to 400, so I'll just call this X again or whatever. But it could be equal to 250 and then you round up. So tape measure marked by millimeters and you've got 18.7 centimeters. So it could be anywhere from 18.65 centimeters to 18.75 centimeters. And again, not including this value, so 18.75 and 18.65. Okay, so a scale marked with kilograms, this could be anywhere from 54.5 kilograms to 55.5 kilograms. Okay, 54.5 less than or equal to X is less than 55.5. Okay. Next, when you're combining many measurements to find the area, perimeter, volume, and some other quantity, you must make the calculations using both the smallest and largest measurements in the range of possible values, calculating the quantity. Using these two extremes will give you the boundary limits. So given the initial measurements, find the boundary limits for each measurement. So floor was measured between 520 and 389 centimeters. What are the boundary limits of the amount of tile needed to cover the floor? So we're talking about area here. Okay, so I'm going to write lower limit here, or lower boundary limit I could call it. Okay, so smallest possible area is going to be 519.5 centimeters by 388.5 centimeters. Okay, and the upper limit is going to be 520.5 centimeters times 389.5 centimeters. Okay, so those are two possibilities. Alright, so you can get anywhere from 201,825.75 square centimeters to 202,734.75 square centimeters. So again, you can do the same thing here. You can do the smallest possible length of fencing is going to be 65.5 meters times 84.5 meters. And the largest possible is 66.5 by 85.5 meters. Okay, so you can work that out yourself. A cylinder, okay, has radius 5 centimeters and height 15 centimeters. So you want to work at the lower limit here. It's going to be, the lower limit of the volume is going to be pi times, so let's call the radius 4.5 squared and the height 14.5. And your answer is going to be in cubic centimeters. Okay, and your upper limit, you're going to get 5.5 squared times 15.5, and you're going to get an answer in cubic centimeters. So let's work that out. Alright, so pi times 4.5 squared times 14.5 gives me 922.45. Okay, and then next we have 0.01. Okay, now so if you take a look at this range is quite large actually. That's quite a big difference. Okay, so these numbers make a huge difference in the final answer, okay? And one reason for that is, well, we have we have this r squared. So the error gets squared and that makes it a really big error. Alright, so you have to be really careful about where your numbers come from when you're doing calculations, because you can have a very large error in your calculations. So we're going to look at percent error right now. So whenever whenever you use measured values, it's not going to be completely accurate. Some errors are going to occur. So we're going to use this formula, all right? And we're going to look at the problem down at the bottom here. Find the error and the absolute percentage error if you estimate that your weight is 60 kilograms when it's actually 58.9. So the error is actually just 60 kilograms minus 58.9 kilograms, which is 1.1 kilograms. So that's the amount of error. We want to get your percentage error, so that's your error, or epsilon, whatever that is. Now be very careful about these numbers. This is approximated measurement. So your estimate is 60. So you put a 60 here. The exact measurement is 58.9. So on the bottom you got 58.9. And this absolute value means you'll make it positive and times 100% to make it into percentage. So let's work that out. Let's do 60 minus 58.9 equals, then divide 58 by 58.9, and we get this number less times 100 to make it percent. So that's actually 1.87%. Okay, so that's not a bad